Good afternoon. My name is Gustavo Anjos. I'm a researcher at Instituto de Telecomunicações in Aveiro. We are in one of our labs where we are developing the nodes for discretion. This setup that you are seeing here is a QKD link between Alice and Bob. So Alice implements the transmitter model and Bob implements the receiver model. So we are seeing the hardware in here. Maybe we can start by explaining the hardware components of the transmitter side of Alice. So this machine that you are seeing here is the host. Everything starts with a KRNG that is installed on the PCI Express slot of the host. This KRNG sends information to the FPGA through PCI Express interface. In a FPGA, we implement the DSP chains that process the random information that generates the key. We can see the transference of that information from the host to the FPGA in this terminal. We can also probe the signals at the output of the DSP within the FPGA. So this is a real-time probe of the signal at the output of the root razor quotient filter. This signal codes the information that is the key information that is then converted to 100 megahertz. This subconversion is done by a numerical control oscillator that is hardwired in the same socket of the FPGA. After converted to the analog domain, the signal is sent to an IQ modulator that encodes the key information in a phase and magnitude of a continuous wave that is generated by a laser. After the IQ modulator, we send the signal at the output of the IQ modulator to an attenuator, an electronic variable optical attenuator that attenuates the signal. We are not yet attenuating the signal to the quantum regime, so we are with a low attenuation, just 10 dBs at this initial battery of tests. The quantum signal is that sent to a WDM coupler and is transmitted to the receiver through a fiber. In this setup, we are using a short fiber of 1.5 meter. At the receiver side, the timing reference and the quantum signal are split by another WDM coupler. The timing reference goes to the FPGA and sets the clocks for the analog digital converters and also to the programmable logic. The quantum signal goes to the detector. We are using a dual polarization heterodyne detector. So in this box that you are seeing in here, first we split the polarizations of the quantum signal and the local oscillator. So the local oscillator is implemented by a laser that is local to the receiver. So they are split, the two polarizations are split by two polarization splitters, and then the local oscillator is mixed with the quantum signal in two polarization couplers. Then the outputs goes to two balanced photodetectors that convert to the electrical domain, and then the two polarizations are sampled and converted to the digital domain by two analog digital converters. Then they are sent to the FPGA. At the FPGA, at this platform, the current version of the platform, we are not running the DSP chain, so the signal, the quantum signal, crosses the FPGA in their host state and is sent to the host through a PCI Express interface. At the host machine, we run the DSP software that we developed in IT to extract the raw key from the quantum signal. We can now show a small test. So we'll start by reading the quantum signal from the channel through the FPGA, running this script. After scattering the quantum signal from the channel, we run the DSP that will allow us to extract the raw key from the quantum signal. So it's this script that you are running. To make the correct compensation of the phase and frequency of the quantum signal, we have to track the phase and frequency of the pilot. So we are performing that tracking now. Then we perform the frame synchronization using a node primal, and we extract the optimal sample. After then these steps, we get the constellation, that is the raw key that we send to the post-processing layer. We can see that we have an AVM, an error vector magnitude of 0.08. So this is the signal that goes to the post-processing layer. As I said, we are not in a quantum regime, otherwise it will not be possible to see this constellation. In this battery of tests, we are using a low order constellation. In the end, we'll use 64 km constellations. In fact, these constellations are already implemented, but for us, it is easier to use a low order constellation to start testing the system. Thank you.